Hello everyone. So the course name is Classical Mechanics of a Single Particle, and today we will talk about the week 6 SN number 6 previous year question paper solution. Okay, so let's start. Before going to the question answer directly, I just want to make a recap of this week number 6, what we in that week number 6 what sir was told. So I just want to make a recap of that. So previously, like in week number 6, let me write here. In week 6, just a simple recap, only for let's say 14 minutes or something. So the recap is like we all know that for free oscillation we are having x double dot plus omega 0 square x equals to 0, and then the solution of x was like a cos omega 0 t plus alpha. So obviously I just want to take exactly same notation whatever sir was taking in his lecture, so that there would be a continuation and there would be no confusion on this understanding and all. So now if I have oscillation plus periodic force, then what was the expression? The expression was this one, f by m cos gamma t plus beta, right? So this is the oscillation plus periodic motion, and what is the solution for that? Solution for that is like a cos omega 0 t plus alpha plus f t by 2 m gamma. Then you can see that there is sine gamma t plus beta, and you can see that this is a cos function and this is a sine function. That means both are pi by 2 phase difference, have a pi by 2 phase difference. Okay, so this is the case, and obviously gamma is what? Gamma is root over omega 0. So just a minute. Yeah, so this is the equation when like gamma is equals to omega 0, that means resonance condition. And if gamma is not equals to omega 0, then x of t is what? X of t is a cos omega 0 t plus alpha plus f by m omega 0 square minus gamma square cos gamma t plus beta. So these things we have already calculated, and these are the solution for this. Now if oscillation plus damping is there, then what will be the solution? The equation is like this one. You all familiar with these things, and as there is no force I am talking right now, then this will be a 0 1. Then what is the expression, final general expression for this? The general expression for this is a e to the power minus lambda minus root over lambda square minus omega 0 square into t plus b e to the power minus lambda plus root over lambda square minus omega 0 square into t. So here we can have three conditions. One condition is the condition is like lambda less than omega 0. This is the underdamped, right? This is the underdamped, and this is a lambda less than lambda greater than omega 0. This is overdamped, and one is lambda equals to omega 0, which is critically damped. So these are things they were talking. And then what will be the solution for a? If we are talking about a, then the solution is like x of t. I'm not going to tell the derivation of that, but the equation is like omega dt plus alpha, where omega d is root over omega 0 square minus lambda square. Now for the b condition, where lambda is greater than omega 0, the equation is like xt equals to a to the power minus lambda minus root over lambda square minus omega 0 square into t plus b e to the power minus lambda plus lambda square minus omega 0 square into t. Okay, and the condition is that lambda equals to omega 0. The solution for that case is like x of t is a plus bt then e to the power minus omega 0 t, or I can write it a plus bt e to the power minus lambda dx, because lambda and omega 0 are equal. Now these are the cases, and sir was discussing that which one is going to decay quickest, and we can see that the the critical damping is decay, like critically damping is quickest decay among all the three conditions. Okay, so this is the thing. Okay, fine. So now what was that? Yes, the another one is that oscillation plus damping plus forced. So for this case, what was the expression? Expression will be like x double dot plus omega 0 square x plus 2 lambda x dot equals to f by m, let's say cos gamma t. Okay, so the solution is like the derivation will be exactly similar, like at the very first we will take the z, then the real part of z and all these things. Then what will be the possible expression of the z is these things, and then the expression is like, I'm just going to take the final expression here. The xt is like here a e to the power minus lambda t cos omega 0 t plus alpha, and e to the minus lambda t is basically nothing but coming from the damping part. Okay, this is coming by from the damping part, and then here f by m, then cos gamma t plus delta in another phase, that root over omega 0 square minus gamma square whole square plus 4 gamma square lambda square. So this is the case of that xt. So now you can see here xcf, the complementary function is e to the power minus lambda t, sorry, let me write here, fine, minus lambda t cos omega 0 t plus alpha, and xpi is important here. Xpi is f by m, then cos gamma t plus b delta divided by root over omega 0 square minus gamma square whole square plus 4 gamma square lambda square. Okay, now you can see that this is the xpi, and now at resonance, now here obviously if I will write here omega 0 equals to gamma, then obviously it will not be a maximum amplitude. So we need to check that where the maximum amplitude is going to happen. So that will be like nothing but the resonance condition. So at resonance means maximum amplitude, and maximum amplitude is what? Amplitude here is f by m 1 by root over omega 0 square minus gamma square whole square plus 4 gamma square lambda square. Okay, so this is the amplitude. So to get the maximum value of these things, then what we will do, let's say this is a b, so db t lambda equals, sorry, not lambda, it will be on gamma, because I just want to know that at which value, gamma value, we are having the amplitude as a maximum one. So this will be 0, and d2b d gamma 2, it should be less than 0, because it is a maximum value. So you can just calculate these things, then we can understand that at which value of gamma we will have maximum value of amplitude. So the gamma is nothing but omega 0 square minus 2 lambda square. So this is the expression for gamma, so that I can have the resonance condition here. Okay, now these are the things sir was discussing here in his calculation, and then there was two problem. This two problem was like chi is like v max 1 divided by v max 2, and he was asking that in which condition the value of chi will be which one. These things are were there, and these were the things. So in the case 1, case 2, he was just calculating what is the v maximum velocity value, and then he just take the ratio of these two velocities, and he has calculated the chi value. So now these are the things. Okay, and another thing was that beats. He was talking about beats for forced oscillation condition basically. So here you can see these things are there. Now the main thing coming after this is like motion of a particle in an electric and magnetic field. So he was talking about three conditions. First condition is that like a constant electric field, no B. Okay, so for this case our the force is like Q into E, and if I am talking about that mv dot equals to Q into E, and here you can see this is the E vector, and then you can see that mr double dot equals to Q into E. So this is nothing but a solution for the simple harmonic oscillator. So the solution is like Q by M Ex t square by 2. If we are talking about E as a x-axis, then C1t plus C2. So this type of solution is there. Now constant B, no E. So this condition is nothing but here our force will be Q into V cross B. So here we can see the equation is like he was talking about one example where B is along B0 z cap, and then V cross B we were talking, and V cross B was nothing but Q in like not Q, I cap into B Vy minus j cap into B Vx. So this type of things are there, right? So then he was just calculating these things, and he was just concluding one thing, that Vx double dot plus omega z square Vx equals to 0. So this is the simple harmonic oscillator in Vx. And what is omega z? Omega z nothing but the gyro frequency, and the gyro frequency value is Qb by m. Okay, it is basically a mode value, right? Qb by m. So that will be different for electron and positron, because Q will be different here for electron and positron. So this is the simple oscillation equation in Vx. Now coming for the Vy as well. So for Vy double dot, I can see one thing that similarly. So like not Vy dot, here we can see the Vy expression directly. So from Vy I can already say the expression of Vy, and as I will get the Vx expression, then from there I can get the x expression. So it is nothing but that x minus x0 is V perpendicular by omega z sine omega zt, and as I can get the Vy from Vx, then I can get the y value, and it is giving me this one, which is V perpendicular by omega z and cos omega z t. Now you can see that I can have one expression, x minus x0 whole square plus y minus y0 whole square is v lambda by omega z whole square, and then cos square theta and plus sin square theta is 1. So now I can write it like rg square. So rg is nothing but gyro radius, and omega z is a gyro frequency. Okay, so these are the things, and rg value is rg has the expression v lambda by omega g. So it is like v lambda by qb and m. So this will be a mode value because rg cannot be a negative value. So these are the cases. Okay, So and x0 and y0 were guiding center. So the equation will be like the motion of this in a constant magnetic field, and the motion of the particle in a constant magnetic field will be like, so here if it is a x and here it is y, and vz was nothing but there is a straight line like thing, because vz dot equals to 0. Okay, so for x and y there will be a circle like thing, and the center will be at x0 y0, but due to the z axis it will go like this along z. So along z it will go, so it is nothing but a helix with angle alpha, let's say, which is tan inverse v lambda by v perpendicular by v parallel. So v parallel is along like vz. Okay, now this is the condition. Now coming to the E cross V drift. So this is the condition when we will talk that E and B both are present, and let's say, like, let's assume, this is just a simple assumption, okay, just an assumption is that E is along, let's say, x cap, and B is along z cap. Okay, so both are perpendicular to each other. So then what will be the solution for this case? If I talk about whole solution, the solution will be like Vx dot, I don't want to write here Vx dot, I can simply write here x is like V0 by omega z sine omega z t plus x0, and then omega y, for y solution I can write here y minus y0 equals to v0 by omega z cos omega z t minus e by b into t. So you can see here x minus x0 whole square plus y minus y prime whole square is equals to y0 prime, let's say. This is v0 square by omega z square. And what is y0 prime? So here I can write here y0 prime equals to y0 minus e by b into t. So now you can see this is nothing but one solution where our center is, let's say, here. This is the case of z, it is y, this is x. So the center is also going to change over time, because the guiding center is a function of t. Okay, so this is going to change. And why it is equals wave drift? Because our velocity is nothing but e by b, which is like vy. One of the component of vy is e by b. So I can write it e cross b by b square mod. So this is the e cross b by b square. So vy is vy plus e by b into t. So I can write it vy plus e cross b by b square. So that's why it is known as e cross b drift. So it is a drifting velocity which can drift the particle. Okay, so these were the little bit recap of whole expressions. I mean, like whole previous week, not previous week, like week number 6. So this is the thing. Now coming to the question. So the first question is question number 1. The angular frequency of a damped harmonic oscillator depends on what? Okay. So first of all, angular frequency of a damped harmonic oscillator. So damped harmonic oscillator I can write here. So for damped harmonic oscillator, the expression is like x double dot plus 2 lambda x dot plus omega 0 square x equals to 0, and there is no force they are talking, right? So for damped harmonic oscillator, this is the expression. Okay. Now what is the solution? So solution was like let's say I'm talking about xpi only. xpi is a to the power minus lambda square minus omega 0 square into t plus b e to the power minus lambda plus root over lambda square minus omega 0 square t, these things, right? So angular frequency of the damped harmonic oscillator. So angular frequency is nothing but angular frequency can be written as this one. So it will depend on what? It will depend on lambda omega 0. Now lambda is a medium damping coefficient. Okay. Now coming to omega 0. Omega 0 is what? Omega 0 is root over k by m. That means our stiffness of the spring ing, and then m is mass of the bob. So these things, so that means our omega, as it is proportional to root over lambda square minus omega 0 square, so omega depends on lambda, which is damping frequency. Omega 0 means k, which is stiffness constant, and mass. So these things, right? Lambda, k and m. So let me go for the option. The magnitude of the external driving force. Okay, so that means our omega as a function of omega 0, lambda as a function of k, m, lambda. The magnitude of the external driving force. External driving force magnitude? No, obviously not. Okay. The mass and damping coefficient only. Mass and mass means m. Damping coefficient is lambda. No, that will not be the case, because it will also depend on the stiffness or the spring constant. So mass and spring constant, that is also not, because there is a lambda is missing. So spring constant k, this is k, and damping coefficient lambda. Yes, that is correct. So it should not be only, because the mass is also there. So the spring constant and the damping coefficient mass on these three strings only. So omega is a function of spring constant and damping coefficient and mass only. Okay. So this is the one. This is the first question. So how we calculated the first question? For the first question, we just knew that what will be the frequency for that damped harmonic oscillator. So the damped harmonic oscillator frequency basically depends on root over lambda square minus omega 0 square, and lambda is the medium damping coefficient, and omega 0 is again depend on that k and m. So omega will be depends on lambda, k and m. This is the thing. Okay, so option number 4 will be the correct option. So this is nothing but omega 0 and lambda, and omega 0 is like k and lambda. Okay, so this is the case for the first question. Now coming for the second question. The natural frequency of a simple harmonic oscillator depends on natural frequency. Okay, fine. So simple harmonic oscillator. Simple harmonic oscillator means this, and the omega value will be root over k by m. That means As you can see that there is no damping or forced oscillation case, so that means it's simple harmonic oscillator without any damp or force. Then our omega 0 is a function of k, which is spring constant, and m, mass. Okay, so natural frequency, now angular frequency, let's say I'm talking about angular frequency was omega 0. Now if we are talking about natural frequency, I can write it as f0, where f0 is nothing but omega 0 by 2 pi. Okay, so the natural frequency of a simple harmonic oscillator depends on the medium, no. The nature of the force acting on the oscillator, no. The nature of the oscillator means like oscillator nature is what, like the spring constant or what, it is also not. But yeah, so as they are talking about the force acting on the oscillator or something, so I can we can think a little bit more on that frequency expression. So now I can tell you one thing, that if only oscillation, that means free oscillation, then our omega 0 is root over k by m. Okay, if with damping, then our omega is proportional to, like omega is a function of omega 0 and then lambda, which we have already seen. Now if with force, then our omega is a function of omega 0 and then gamma, which is the force, the frequency of the forced oscillation. Now if I talk, if with damping and force, then our omega is a function of omega 0, lambda, gamma. Okay, so our omega is a function of natural frequency, and natural frequency means obviously it will be again the function of spring constant and mass, k by m, right? And lambda is the damping coefficient, and forcing frequency. So these three things. Now coming to the option, the medium. Okay, the medium is fine, but if it is talking about with the force also, then only medium will not be the correct one. The nature of the force acting on the oscillator, that is also fine, but it is not only the case, and medium will also be there, and the natural frequency will also be there. The nature of the oscillator, yes, that is fine, but we have to take care of the forcing frequency as well as the medium also. Both the medium and the nature of the oscillator, okay, that is also fine, but force is, where is force? Force is missing here. The medium, the oscillator, and the nature of the force acting, yes, that is the correct one. Medium, which is lambda, oscillator omega 0, and the forcing acting means gamma. So these three should be there in our simple harmonic oscillator, which is with damping and forced as well. Okay, so if I talk about three things together, then I will have the natural frequency or angular frequency, whatever that will be. I think I should not write here omega 0, it should be simply omega or f. Okay, so it will be omega by 2 pi. Okay, so now, yeah, so question number 3. In an overdamped system, displacement of the particle oscillates with increasing amplitude, decays exponentially without oscillating, is always zero, oscillates but remains bounded. Okay, overdamped system. Let me the displacement of the vector. Okay, so overdamped. So for overdamped means lambda is very greater than omega 0. Okay, and what is our xt? Xt is a e to the power minus lambda square minus omega 0 square into t plus b e to the power minus lambda plus root over lambda square minus omega 0 square into t. Now you can see here, if I talk about this term, and the condition is lambda is very greater than omega 0. So what will be this one? This one will be a positive term. Okay. So that means we will end up with simply these things. Minus lambda t, let's say, or let's say I can write here e to the power minus lambda t, a e to the power root over lambda square minus omega 0 square t plus b e to the power minus lambda square minus omega 0 square t. So this is nothing but decaying function with e to the power minus lambda t, as well as both of the terms are something which, this is exponential, but this is again exponential increasing, exponentially decreasing, but as a whole these will be multiplied with a exponentially decaying function. And also omega is very greater than lambda is very greater than omega, so obviously this one will be dominating here. So what will be the nature of this case? The nature of this is like, here it is t, here it is let's say x of t, so it will be simply decaying. Okay, due to the e to the minus lambda t term. So now the displacement of that particle oscillates with increasing amplitude. No, it is not correct. It decays exponentially without oscillation yet. This is the correct. Is always zero, is also not, oscillates but remains bounded. No, this is the case for the case of that underdamped motion. Okay, we will talk that one later. This will be oscillate but remains bounded in a some value. Okay, so but this is not the case for overdamped. For overdamped case, we will have only the decays exponentially without oscillating. Okay. Now yes, this is the case. Underdamped motion without forcing. Okay, without forcing means our f equals to 0. So without forcing means obviously that means only damped condition. And they are asking about underdamped. What is underdamped here? Underdamped means our lambda is less than omega 0. Now you can see what was our xt. Our xt was a to the power minus lambda plus minus root over lambda square minus omega 0 square into t plus b e to the power minus plus lambda square minus omega 0 square into t. Now you can see here our lambda is less than omega 0. So lambda square minus omega 0 square, that will be an imaginary one, right? So I can write it like a e to the power minus lambda, here I can write it as I root over minus 1 as I, then omega 0 square minus lambda square into t plus b e to the power minus lambda plus I omega 0 square minus lambda square into t. So it can be written as like I can take out e to the power minus lambda t, then a e to the power I something, let's say omega dt plus b e to the power minus I omega dt. What is omega d? Omega d is nothing but root over omega 0 square minus lambda square. So I can say here that e to the power minus lambda t and some another coefficient, another constant a, and then cos omega dt plus, let's say, alpha, any other constant, initial condition, initial phase. So our xt is coming as a to the power minus lambda t cos omega d alpha omega dt plus alpha. So that means what? This is a nothing but a oscillating function, but with a amplitude which is decaying with time. So what will be the nature for this case? The nature is like this one. Here it is t, this is xt. So xt value can go from +1 to -1 because cos has -1 to +1. So it can be like that only, and this will be a boundary for this case. And within that boundary, what is the value? The value is like, so let's say here the t is 0. So if t is 0, that means I can have e to the power 0 is 1. So that means a cos alpha. That means it's a cos function. But as the time increases, this amplitude will give me a depletion in that amplitude case. So it will be like that only. And it will not stay here, it will go in at infinity to make a 0. So this type of plot will be there. Now you can see the option, the amplitude decreases with time. Yes, that is correct, but it is not telling the full expression. Okay, fine. The motion, okay, let me not put across here right now. The motion is not periodic but oscillatory. Okay, the motion is periodic but not oscillatory. No, that is not correct, definitely. The frequency of the oscillation is different from the natural frequency. Yes, that is fine. The mechanical energy is conserved. No. And this is also fine. The motion is not periodic but oscillatory, and this is also fine. That amplitude decreases with time. So basically nothing but this is the correct one. The motion is not periodic but oscillatory. That is also not correct. The frequency of the oscillation is different from the natural frequency. Yes. Okay, let me do one thing. So for underdamped case, this is correct because the frequency of the oscillation is different, which is like omega or omega d or something. So what was that? That was like root over omega 0 square minus lambda square. From the natural frequency, it is different, and the motion is not periodic. It is not periodic because after some time we are not getting the same frequency plot. So this is correct, but oscillatory. Obviously, it is an oscillatory motion like that. And amplitude decreases with time. That is correct because we can see that after some time amplitude is going to decrease. And the mechanical energy is conserved. No, because here we can see it's not basically a conserved quantity. The energy is getting decreased. So for this case, this is correct, this is also correct, and this is also correct. Okay. So underdamped motion, basically we have to remember that for overdamped this is the case, for underdamped this is the case. And for critical damping also this is the case, because there is also something a plus bt to the power minus lambda t, something like that, but as a whole e to the power minus lambda t is there, and there will be no oscillation. Only for the underdamped case, underdamped, so for the underdamped case only there will be a oscillation, that's it. And for these two there will be no oscillation case. Okay. Okay, so now this is a question. So for an oscillator without damping, okay, first of all it is telling that without damping, so we will not take care about gamma is 0, so it is not, or a, oh no, sorry, that I can go to damping is no here, so that means lambda is 0. So What is the expression here? The expression is nothing but x double dot plus omega 0 square x equals to f by m cos gamma t, something like that. Only first. And what is the mass? Mass is like 0.5 kg. What is stiffness? Stiffness is like K, which is 2 Newton per meter at t equals to 1 second. Okay. What is the amplitude at resonance for the particular solution of displacement if the periodic force amplitude is given by this? Okay, so first of all, what is the solution? The solution is something xcf plus xpi. Okay, so this is the solution, and the solution is xcf is there and xpi is there. So if I talk about that xcf and xpi collectively, so this will be xt, as you can see here, as it is at the condition for the resonance one, right? So they are talking about the condition at resonance. So this will be a cos omega 0 t plus alpha. Then there will be this one 2m gamma, then sine gamma t plus beta, or something like that. So here you can see, if I will talk about xpi, the xpi will be ft by 2m gamma sine gamma t plus beta. Okay, so the amplitude is like ft by 2m gamma at resonance. Okay, so this is the amplitude at resonance. So now let me write here all the things, whatever it is given. So first of all, what is given here? The amplitude, the periodic force amplitude is 1/4 Newton. Okay, so 1.4 Newton. AM is 0.5 kg, and then here it is gamma, and at resonance gamma is omega 0, which is root over k by m, right? So I can write here gamma as root over k by m. So the amplitude is ft by 2m omega 0, or ft by 2m gamma. It can also be written as am is 1.4, t is 1, divided by 2 into 0.5 into root over k root over m. So it is 1.4 root over 0.5 divided by 2 into 0.5 is 1 into root over k. K is what? K is given as 2. Yes, 2. So it is 1.5 into root over 1.2 into 2. So 1.5 divided by 2, which is 0.7 meter. Okay. So this is the amplitude at resonance. Amplitude at resonance for only forced oscillation, no damping, with t equals to 1 second, m equals to 0.5 kg, k equals to 2 Newton per meter, and f equals to 1.4 Newton is 2m omega, which is like, okay, maybe we should consistent with the nomenclature. 0.5 and then root 2 root 0.5. So this is as a whole coming as 0.7 meter. Okay, so this is the case for the value of that amplitude. Okay, my charge is not there, so just a minute. Now coming to the next question. Yes. A mass spring system has mass equals to m 1 kg, stiffness k. If a sinusoidal force of amplitude f0 is applied, what is the steady state amplitude at resonance? Okay, similar question is there. So given m equals to 1 kg, okay, k is 9 Newton per meter, f0 is 1.8 Newton, and at resonance they are talking. Yes, so at resonance we all know that omega 0 is equals to gamma. No damping case is there, so that means we will not take care about the lambda value. So that means our gamma is root over k by m, which is equals to k is 9 divided by 1, so it is 3. Okay, so steady state amplitude f, I should write here like that, 2m omega 0, or it can be also written as f0 2m gamma, where t equals to 1. So sorry, f0 is what? f0 is 1.8. 2 into 1 into gamma. Gamma is what? Gamma is 3. So you can see it is 1.8 divided by 6, 0.3 meter. So 0.3 meter is the amplitude for the only forced oscillation, no damping, with m equals to 1 kg, k is 9 meter per second, and f0 is 1.8 Newton at resonance condition. Okay, so it is coming as 0.3. So this is the answer. So this will not be the answer, this will not be the answer, this will not be the answer. So the expression is f0 t divided by 2m omega 0, or f0 t by 2m gamma, and gamma is this k by m. Okay, so this is the case for question number 6, I think. Yeah, now we can go for question number 7. Okay, which of the following are true for the resonance in the case of a forced periodic oscillator without any effect of damping? So first of all, we just need to write here only forced oscillation, no damping. In that condition, our equation of motion is this one. right? And then our xt was what? Xt we were talking just before some time, and that was like some CF and PI will be there. Okay, so it will be A cos omega 0 t plus alpha plus ft by 2m omega 0 sin gamma t plus beta. So this was the case. Okay, and I can write it like xcf plus xpi. Now coming to the question. Which of the following are true for the resonance in the case of a forced periodic oscillator without any effect of damping? Natural frequency, okay, is equal to the periodic force frequency. It is okay for the resonance case. Okay, for the resonance case, I should write here. For resonance, gamma equals to omega 0. Okay. So for resonance, the natural frequency which is omega 0 and periodic force frequency gamma, and this should be equal. That is correct. The force is in phase with the displacement. No, this is not correct, because you can see here the displacement is ft by 2m omega 0, and here it is sin gamma t plus beta, and it is a sine function, but our forced oscillation is in cos function, right? So that means it is not in phase. There is a pi by 2 phase difference. The force amplitude decreases monotonically with time. No. Okay, increases monotonically with time. Yes, that is correct. Why that is correct? Because the force amplitude is no, not force amplitude. The displacement monotonically increases with time. That is correct. So force amplitude we are not talking about here. Force amplitude was simply that f0, but f0 is a constant one, but displacement monotonically increases with time. So this is a displacement amplitude which is ft to m omega 0. So right, you can see that this is proportional to t. So monotonically increases with time. The mechanical is not conserved. Yes, this is also correct, because it is getting absorbed by the system. So these are the things. So now the main thing here is that omega 0 equals to gamma, and then the force is obviously in phase difference of pi by 2. Okay, the force amplitude increases monotonically with time. That is not correct, but displacement is monotonically increases with time, because it is a function of t only. The mechanical energy is not conserved. That is also fine, because as the amplitude is getting monotonically increasing, that means the system is absorbed the energy. That is the thing. So mechanical energy is not conserved here. Okay. So this one, for resonance in a lightly damped forced oscillator, which is the following is true. Now coming here, resonance, lightly damped forced oscillation. So what does this means? Lightly damped forced oscillation. So first of all, damping is there, forced is also there. So it is x double dot plus omega 0 square x plus 2 lambda x dot equals to, let's say, f by m cos gamma t. This is the equation of motion. So now here lightly damped forced oscillation. So lightly damped means like our damping is little bit smaller. Okay, the amplitude what I can get, or let's say the solution for this question I can get from the calculation, and this is a to the power minus lambda t cos omega 0 t plus alpha plus f by m cos gamma t plus b, let's say delta or beta, divided by root over omega 0 square minus gamma square whole square plus 4 gamma square lambda square. So now you can see here from xpi I can get f by m something like cos gamma t plus delta, but here omega 0 square minus gamma square whole square plus 4 gamma square lambda square. So at resonance, resonance means the amplitude is maximum. So when the amplitude will be maximum, d of, like this is let's say I can write here b is f by m omega 0 square minus gamma square whole square plus 4 gamma square lambda square. This is my b. Okay, so now this is 0. So if I calculate this one, then it will be like f by m, then 1 by x to the power minus half, right? So it is something like x to the power minus half. So here it will be minus half into I can write it like this. I'm talking about this, right? So this whole as x to the power minus half. So x to the power minus half, minus half, x to the power means omega 0 square minus gamma square whole square plus 4 gamma square lambda square whole to the power minus 3 by 2 equals to 0. So this whole term will not be 0. So this will be 0. So now gamma square minus omega, sorry. Okay, so gamma square gamma square minus omega square whole square plus 4 gamma square lambda square is 0. Okay, and also there will be one thing that this is not a x, so there will be a derivation of that. So it will be like 2, then omega 0 square minus gamma square, again minus 2 gamma, right? So this whole, then I can write it like, so 2 into omega 0 square minus gamma square into minus 2 gamma plus 4, and again this one is also there, 4, then gamma square is coming as 2 gamma and then lambda square. So 4 into 2 gamma lambda square equals to 0. Okay, so then you can see here that omega 0 square minus gamma square into gamma plus 2 gamma lambda square equals to 0. So gamma will not be 0. So that means omega 0 square minus gamma square plus 2 lambda square equals to 0. So from there I can have gamma square equals to omega 0 square this was there? Yes, plus 4 plus minus. Okay, here is a minus sign. So that means there will be a minus. So I can write it like minus omega 0 square my laptop is not working. Yeah. Okay. So minus omega 0 square plus gamma square plus 2 lambda square equals to 0. So gamma square will be here it will be omega 0 square minus 2 lambda square, and gamma is root over omega 0 square minus 2 lambda square. So this will be the condition for that amplitude as a maximum, which is the resonance condition. Displacement is maximum when the forcing force matches. Okay, that means our gamma is matches with omega square minus 2 lambda square, what we already got. So this is correct. Okay, now come here in the next option. Mechanical energy increases exponentially. Mechanical energy increases exponentially. No, how we can conclude that one? So this is not correct. The system cannot oscillate. What is the expression here? Mechanical energy increases for first, but okay, the thing is that due to forced oscillation, okay, maybe I can write it whole things not okay, here. So this is the gamma as root over omega 0 square minus 2 lambda square, and the first one is correct. Now what about mechanical energy increases exponentially? So this is not correct. Why? I can tell. Just a minute. Yeah. So due to sorry. Due to forced oscillation, the mechanical energy increases, right? But due to damping, the mechanical energy decreases. So basically mechanical energy is getting balanced. Okay, so it is getting balanced. So now whatever the option was there, that mechanical energy increases exponentially, that is not correct. Now the system cannot oscillate. No, it's wrong. Why? We can see that our xt was a to the power minus lambda t cos omega 0 t plus alpha plus f by m cos gamma t plus delta divided by root over omega 0 square minus gamma square whole square plus 4 gamma square lambda square. So as a whole, this has an oscillatory term which is cos gamma omega 0 t plus alpha and cos gamma t plus delta. So as a whole, the system will oscillate, and the main thing is that the system oscillates most importantly resonance, the oscillation is maximum, because that is the meaning of oscillation, that at the resonance the amplitude will be maximum. So the amplitude will be maximum for the oscillation resonance case. This is not correct, that the system cannot oscillate. Phase difference between force and displacement is always pi by 2. No, that is also not correct, because I can show you that. Yeah, so here you can see our force was what? F0 by m cos gamma t. So here it was a cos function. There is also cos function, there is also cos function. Oh, but obviously depending on this whole term, it will change. But as a whole, it is not like that always it will be a pi by 2 phase difference of displacement and force. So this is also not correct. So only the correct option is displacement is maximum when the forcing frequency matches root over omega 0 square minus 2 lambda square term. So which we have already also discussed here, and it is coming that gamma equals to this omega 0 square minus 2 lambda square. Okay. Okay. Now question number 9. Yeah, so for this case we will basically dive into the condition where that the motion of a particle in presence of a constant magnetic field or constant electric field or E cross B drift. Okay, so now come to the question here. The charged particle of mass m. So what is given? Basically given is m equals to 9.1 into 10 to the power minus 31 kg, q 1.6 into 10 to the power minus 19 coulomb, magnetic field 2 Tesla. The gyro frequency is what? So I told you previously when the class was started that if I have a constant magnetic field, here you can see there is no electric field they are talking. So a constant magnetic field, it is in a constant magnetic field. And also if it is in a electric field also, but the gyro and constant electric field is also there, then the gyro frequency, they are talking about the gyro frequency. Gyro frequency is omega g or something you can take. So it is qb by m, and this is the mod value. Why mod value? Because q can be plus or minus, so it is mod of qb by m. But you can see that here they are talking about hertz. So hertz means the gyro frequency will be in the natural unit. So natural frequency. So it will be like simply f g, which is omega g by 2 pi. So it will be qb by 2 pi m. Okay. Now what is given here? Q is given as 1.6 into 10 to the power minus 19 coulomb. Very good. B is given 2 Tesla. M is given 9.1 into 10 to the power minus 31 kg. Now what is gyro frequency? Gyro omega g, gyro angular frequency if I talk, then it is qb by m. So if I put all the values, and you can see that all the things are in it's a unit kg, Tesla and coulomb, so all the things are fine. So I don't need to change the unit and all. So it will be 3.2 divided by 9.1, 10 to the power minus 19, 10 to the power 31. So this will be like of the order of, I can say like 0.35 into 10 to the power 12 radian per second as omega g we are talking. Now they are given the answer as hertz, so it is like omega g by 2 pi, which is 0.35 into 10 to the power 12 divided by 2 pi, which is nothing but 5.6 into 10 to the power 10 hertz. Now come to the option. 5.6 into 10 to the power 10. Okay, so this one, and all, actually this will be in superscript, and all the terms are given in plus 7 hertz, so which will not be the correct option. The correct option will be 5.6 into 10 to the power 10 hertz. Okay. Okay, now we can go for the next question. So for a particle of mass m is given 10 to the power minus 15 gram. Q is given 1.8 into 10 to the power minus 19 coulomb. B is given 1.5 Tesla. Again you can see that they are asking that gyro frequency and it is given in hertz. So omega g gyro angular frequency, this is QB by M. So if I write here Q is given in 1.8 into 10 to the power minus 19. 1.8 into 10 to the power minus 19 coulomb into B is given as 1.5 Tesla. Now M is given 10 to the power minus 15 grams. So obviously I have to write it like 10 to the power minus 3 then kg. Now you can see 1.8 into 1.5 minus 9 10 to the minus 19 plus 18. So if I calculate this, then it will be like 0.4297 10 to the power minus 1. So it is 0.04. Oh, actually I am talking, okay, let me write here the actual value. So it is like 1.8 into 0.15. Okay, so let me multiply 1.8 into 0.15. So it is 0.27. But now they are talking about f g, which is omega g by 2 pi. So if I do, that means if I divide that by 2 into pi, 0.0429. okay, 0.0429. So I can write it as 0.043 and it will be in hertz. Okay, so the answer is 0.043 hertz. So none of these options should be correct and the fifth one will be the correct one. So what we have used, we have used the expression as omega g is QB by M and Fg is QB by 2 pi M. Okay, this is the gyro frequency. Okay, so now coming to question number 11. In a crossed electric and magnetic fields, that means E and B are perpendicular to each other. Okay, so in cross electric and magnetic fields, the drift velocity vector is what? Okay, very good. When E and B are perpendicular to each other, then the velocity, specifically drift velocity, is E by B which is E cross B by B square. So you can see that our VD, which is drift velocity, has the direction along E cross B direction. Okay, so you can see this is the thing, E cross B. This is not correct, this is not correct, this is also not correct. Okay, so the in a cross direction magnetic field, the drift velocity vector is along E cross B, because I can have that E by B and E cross B by B square mod. Okay, now coming here, in the presence of constant electric and magnetic fields mutually perpendicular to each other, the drift velocity is. Again, I can see here the similar question. Constant electric and magnetic field means okay, and E and B mutually perpendicular. That means again this. So there will be VD and VD will be E by B, which is E cross B by B square mod. So in presence of constant electromagnetic fields mutually perpendicular to each other, the drift velocity is directly proportional to the mass of the particle, perpendicular to the magnetic field, perpendicular to the electric field, perpendicular to the magnetic field is wrong, perpendicular to the magnetic field is wrong. Of different signs for positively and negatively charged particles, no, because there is no Q terms here. Of constant magnitude, that is correct. Why constant magnitude? Because you can see here our E is a constant, B is a constant, so E plus B by B square or E by B, both will be a constant value. So drift velocity will be a constant in magnitude. Okay. Okay. Okay, the amplitude at resonance in a damped harmonic oscillator. A damped harmonic oscillator, right? For a damped harmonic oscillator means the resonance is there. That means what? And resonance they are talking, that means obviously they are talking about forced oscillation. So our xt was you can see here these terms will be like F by M right. So at resonance, what was happening at resonance? We got the answer that gamma was root over omega 0 square minus 2 lambda square, where lambda is damping factor, but the damping coefficient. Okay, so this is the damping coefficient. So the thing is that at resonance, if I put the gamma equals root over omega 0 square minus 2 lambda square, our amplitude will be F by M root over So let me write here this. So what will happen? Omega 0 square minus gamma square. So it will be this. So it will be simply 2 lambda square. Gamma square is omega 0 square minus 2 lambda square. Okay. So as a whole, this will give me 4 lambda square, 2 lambda square. Okay. 4 lambda square omega 0 square minus lambda square. It is 2 lambda. Then omega 0 square minus lambda square is what? Square minus lambda square, 2 lambda square. Okay, fine. So there is nothing. So it is like root over omega 0 square minus lambda square. So as a whole, our amplitude will be f by m 1 by 2 lambda 1 by root over omega 0 square minus lambda square, and that will be our maximum amplitude. Now you can see that the maximum amplitude is finite. Okay, it is a finite and also maximum. Right. So why I am talking about it is a maximum, because if I do that d2b d gamma 2, okay, so this will be this. So minimum means negative and maximum means it will come as positive. So let me do that one as well, or what? Yeah, this is fine. So it will be maximum but finite. It will not be the infinite, it will not be the zero, and it will not be the negative infinite. So the amplitude at resonance in a damped force harmonic oscillator is maximum but finite. Maximum and finite. Okay. Because we will put the expression that omega square gamma square equals to omega 0 square minus 2 lambda square. And this is coming from this condition. Okay. The amplitude of the resonance of a forced damped harmonic oscillator is described by the differential equation this. This is very like well-known equation, as we have already discussed that one. The amplitude at the resonance. Okay, fine. F by m cos gamma t. Okay, this is well-known equation, and the expression is like to the power minus lambda t cos, let's say omega 0 t plus alpha. Then so it will be at it will be at resonance condition, right? So without resonance, what will be that one? That B will be there. And what will be the expression for B here? The expression for B is nothing but this, f by m cos gamma t plus delta root over m h minus delta square whole square plus 4 gamma square lambda square. So that will be a maximum value, right? So whole will be maximum means this should be a minimum value. So the amplitude will be, we have verified right now, this will be this one, but still I just want to write here. You can see that B is like f by m this, so dB d gamma equals to 0. So you can see here that this whole derivative, so it is f by m is there, then minus half omega 0 square minus gamma square whole square plus 4 gamma square lambda square to the power minus 3 by 2, but this is not the x, the x is like 2 into omega 0 square minus gamma square into minus 2 gamma plus 8 gamma square 8 gamma into lambda square, that will be 0. Now you can see that this whole will not be 0, so simply 2 omega 0 square minus gamma square minus 2 gamma plus 8 gamma lambda square is 0. So this is minus 4 omega 0 square gamma square plus 8 lambda square equals to 0. Omega 0 square minus gamma square plus 2 lambda square equals to 0. So I can write omega 0 square minus gamma square equals to 2 lambda square, and gamma square equals to omega 0 square minus 2 lambda square. So if I put this value, then B is like f by m root over omega 0 square minus gamma square means omega 0 square plus 2 lambda square whole square plus 4 gamma square lambda square. Now you can see f by m 1 by root over 4 lambda to the power 4 plus 4 lambda square, gamma square is what? Gamma square is omega 0 square minus 2 lambda square. So this will be f by m root over 4 lambda to the power 4 4 lambda square omega 0 square minus 8 lambda to the power 4. So this is 4 lambda square omega 0 square minus 4 lambda to the power 4. So this will be f by m 4 lambda square omega 0 square minus lambda square. So this is 2 lambda omega 0 square minus lambda square. The answer is f by 2m lambda root over omega 0 square minus lambda square. Now we can see the option f by m 2 lambda root over lambda omega 0 square minus lambda square. So this is not correct, this is not correct, this is not correct. Square minus lambda square. Okay. Yes. Okay. Now come to the next question. A charged particle moving in a uniform magnetic field with no electric field. Okay. B is there, but no E. So we have already calculated these things when B is there. B is there means, that means, let's say our Q into V cross B will be there as a force. So, and let's say B is in Z cap. So V cross B is I, J, K. So it is Vx, Vy, Vz, 0, 0, B. So you can see here that I cap is B, Vy, J cap is minus B, Vx, and K cap is 0. So V cross B is I cap B, Vy minus J cap B, Vx. So if I want to write here, like for x-axis, x double dot or mx double dot equals to fx. So for fx it is q into v cross b of x. Okay, so it will be simply qb v y, right? So I can write here vx dot equals to qb by m vy. Similarly, vy dot, here you can see there will be a minus, so minus qb by m vx, and vz dot is q into v cross b z component. So v cross b z component is 0. So vz is a constant. Then we can see that vz is simply like one line. Now coming to the, like, let's say z is like ct plus d or something. Okay. Now coming here for vx dot and vy dot. So vx dot is qb by m vy, vy dot is minus qb by m vx. Now you can see that these two are coupled equations, so I can write it like vx double dot qb by m vy dot, and vy dot is what? qb by m minus qb by m vx. So minus q square b square by m vx. So it is nothing but vx double dot plus omega z square vx equals to 0. Omega z is qb by m. So this is a equation for simple harmonic oscillator in vx. So our vx will be like, let's say some v0 then cos omega z t. Okay, now vx, then x will be like something v0 by x is what? X will be simply a constant v0, yes, v0 by omega z, then sine omega z t. Now if I got the vx value, then vy can also be calculated. Vy is what? Vy dot minus qb by m into vx. So minus qb by m v0 cos omega z t dot t. So vy is qb by m v0 cos integration is sine omega z t divided by omega z, and qb by m is omega z by omega z v0 sin omega z t. So this is minus v0 sin omega z t. So this is v0, so y is minus v0 sin omega z t integration, so it is plus v0 cos omega z t by omega z plus y0. Here also something as x0 will come, so this will be x minus x0 is v0 by omega z sin omega z t, y minus omega 0 is this. So if I calculate x minus x0 whole square plus y minus y0 whole square, it is v0 square by omega z square, and let's say this is rg square. So this is nothing but a circle of radius rg with center x0 y0 in xy plane, but due to the z it will be gliding and helix like thing along the z-axis. So let me come to the option. A charged particle moving in a uniform magnetic field with no electric field will move in a circular path. It will not move in a straight line, it will be not in a rest and oscillate back and forth. It is also not correct. So moving in a circular path, that we can see, because here we can see that x minus x0 whole square plus y0 y minus y0 whole square equals to v0 square by omega z square equals to rg square. This is the equation of circle. Okay. Now come here. I think I can take you this question as a homework, so that we can you people can do a little bit, and if it is not be done, then we can talk in the next class. So maybe I can go for the next question. Yeah. An oscillator has a natural frequency of 25 Hz. When damping is applied, the frequency drops to 20 Hz. The damping coefficient is what? Okay. So given omega 0 is 25 Hz. I think it is the yes. Damping is applied, the frequency drops to 20 Hz. Okay. Damping lambda is applied. So now our omega becomes 20 Hz. Okay, fine. So here basically our omega is lambda square minus omega 0 square, right? As we can see in the equation as well. So now I can have the value of lambda from there. How? Because omega is root over lambda square minus omega 0 square, and then this, so lambda square is omega square plus omega 0 square. Omega was 20 Hz, omega 0 is 25 Hz. Then you can see it is 400 plus 625. So lambda is 400 plus 625 root over of L 32.01 Hz. No, actually it should be like, let me do one thing. Yeah, so the damping is getting lower, right? So that means it should be this one, omega 0 square minus lambda square. If it is like that, then because it is not a overdamped case, it is a underdamped case, right? So our omega is omega 0 square minus lambda square. So omega square is omega 0 square minus lambda square. So lambda square is omega 0 square minus omega square. So this is 25 whole square minus 20 square. So lambda square is 625 minus 400 is like 225. So lambda will be like root over 225, which is 15 hertz. So this is the condition for the underdamped case. Okay, it is not a overdamped case. Where lambda is less than omega 0. So this is a 15 hertz. Actually, whether it is underdamped or overdamped, you can see by seeing the options. Here you can see that natural frequency was 25 and none of the option is greater than 25. So that means it will be an underdamped case. So we have to take that lambda is less than omega 0. So accordingly, we will just put the expression. Okay. Okay, now we can see that the natural frequency of an oscillator is omega 0 is 20 hertz, while its frequency in the presence of a damping lambda is given as 16 hertz. So here obviously we can see that omega 0 is greater than lambda, that means lambda is less than omega 0, which is the condition for underdamped case. So what will be the value of the damping coefficient? Okay. Damping coefficient in the presence of the damping is okay. Now while the frequency in the presence of damping, so this means omega is 16 hertz, and by seeing they are asking that what is the value of lambda. So the lambda, obviously you can see that all the terms are less than 20 or equal to 20 or something like that. So we can see that lambda is less than omega 0, right? Okay, so I can take that. So lambda is less than omega 0, that means omega will be root over omega 0 square minus lambda square. So omega is given as 16 and omega 0 is 20. 16 and 20. So 16 square equals to 20 square minus lambda square. So lambda is this 12 hertz. Now you can see that this is possible because we are having that underdamped case.